Alright, try 2 with going over some information about light. Light first consists of waves, and we'll look at, for instance, our visible light and the waves that we can have in that. But when we look at light, there are some vocabulary words that we need to be aware of. First of all, one of them is wavelength. This is the length of a complete wave. And then we have frequency, and that's how many waves can pass a certain point during a certain period of time. The higher the frequency, that means that the wavelength has to be shorter because you have to fit more waves in a certain amount of time. We measure this in hertz, so when you see Hz, that is our metric unit for being able to deal with frequency. And then we also have amplitude, and that is the distance kind of from the midpoint, the origin, either high to the crest, the tallest, highest point, or down to the trough, the lowest point. So here's amplitude again, since we just finished that. If we were to measure this one from the origin down, that would also be the same. But when we take a look at this, we have both of these are going to start at the exact same time. So the length of time is identical. You're going to see that they finish at exactly the same time, but yet the one at the bottom looked like it was moving faster, and the reason it looks like it was moving faster is because it has a higher frequency. The only reason it has a higher frequency just means that it can have more waves passing in a given point of time. So notice that the wavelength there is a lot shorter than the wavelength for the top example. And because of the higher frequency, we also have higher energy. So higher frequency is going to equal higher energy. These 3 examples are just showing you, again, the same time period, but because the wavelengths are from the wavelength is very large to smaller and even smaller. We have different hertz, different frequencies. The one at the very top is only 4 hertz because there are 4 cycles per second. The middle one has a higher frequency of 12 hertz because it has 12 cycles per second, and the bottom one even higher frequency because those wavelengths are really short, and 36 cycles per second. When we look at electromagnetic waves, we're looking at radio waves, microwaves, things that we can see, visible light, also getting into X-rays. Many of you may have had an X-ray taken at some point. And you can see that the wavelength for radio, TV waves, the wavelengths are really large, so the frequency is going to be smaller, whereas you get into X-rays, which are a lot higher energy. Notice that the wavelength is a lot shorter, so the frequency is a lot higher. The type of light that we can see, visible light, red, orange, yellow, green, blue, indigo, violet, this range right here is, you're looking at frequencies just a little past 1 × 10 to the 14th hertz. So that's a lot of zeros. Okay, we're looking at frequencies that are really high. Sunlight, when we talk about a spectrum, we're looking at what colors are actually there when you separate them with a prism, and the colors of sunlight are actually represented with the acronym, you might have heard of it before, Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. And we can get that white light by having that light pass through this prism. The prism kind of breaks the light up into the different wavelengths, and you have increasing wavelength over here, and the shorter wavelengths would be down on the other side, so increasing energy. Now when we look at the atomic spectrum still again is talking about how things break into different wavelengths when they pass through a prism. But when we're looking at the atomic spectra, we're doing that with electrons from atoms. So we know that electrons are supposed to follow the Afubu principle, and they are supposed to be written in their lowest energy first before you move up to higher energy. And when we follow that rule, we would say that the electrons are at a ground state. So for helium, 2 electrons, so ground state would be 1s2, and that would be the lowest energy full before we tried to move on, and we don't need to. Now, electrons can jump up to higher energy, If they absorb or gain energy, then they can move up to a higher energy level. We call that an excited state. So for instance, in our example now, one of these electrons has gained enough energy that it's moved up to the second energy level, the s orbital. We're not following the Afubu principle anymore here because we haven't put our electrons into the lowest energy level first. Now, what's really awesome is that when they're in an excited state, they are very unstable, and so they're not going to stay there for very long. They're going to fall back to the lower energy, to the ground state, and when they do, they release light. As they're losing that energy actually has to be released in some type of energy, and so it comes across as light. You need to know how light is formed. That is definitely has been an essay question in the past. So visually wise, this is how we're going to talk about this. This is a lithium atom. We are in lowest ground state here, where we filled up the 1s2 here with the 2 electrons, and then we've moved up to the second energy level, and they only have 3 electrons, so that's as low as we can go. But lithium can gain energy, and when it does, that electron in the second energy level can actually jump up to a much higher energy level. That's not where the light is created, though. It has more energy. That electron here is, bouncing all over the place, lots and lots of energy. When it emits light is when it loses that energy. When it loses the energy and drops back down to the ground state, that is when light is given off. Right there. Light is given off when it's dropping back down to ground state. Just another visual example here of our excited lithium atom as it falls back down to ground state. We have this red here. This is the light that we visually can see. Lithium lets off a red color. Not every atom lets off red. It's unique to lithium, and every atom has its own color, or variation color that it releases. So this is a way that we can tell atoms apart as well. We also can use this whole idea of atoms giving off different colors of light with our neon lights, for instance. It doesn't have to be a neon gas, but it could be any type. We have any type of atom in gas form we could put into these tubes, put electricity through them, which makes their energy a lot higher. Again, they're unstable, so as that electron energy falls back down, we get whites, greens, reds, all sorts of different colors depending on the type of gas that they've used within that tube. We're going to be looking at this idea of the atomic line emission spectra, but this is something again that Niels Bohr kind of contributed, was when he was building his model of the atom. He based it off of the line emission spectra and these excited atoms and gaining and losing energy and the type of color it gave off. The problem was that at the time this model only worked for hydrogen, so it wasn't something that we could apply to every single one of the elements on our periodic table. As far as the line emission spectra, we know that the excited atoms are going to emit light when they are losing energy, and the wavelength of light will depend on the element. So each element will have its own spectra unique to it. Some things that we need a light source, definitely, and we need a prism so that we can detect the different light colors there, the different wavelengths that we get for that particular atom. When we do this for hydrogen, hydrogen is put into a cathode ray tube, electricity is hooked up to it, and we were going to get a certain color. Now if we have a prism, that color hits, we can see that hydrogen's actually broken up into 4 different colors, 4 different wavelengths of color, and that's unique only to hydrogen. Here's some other examples. Here's the hydrogen example again, but here's mercury, here's neon. Each one is unique, each one's different. We still see some of the same colors, like this one has red, this one has red, but the wavelength of red is different. So they are unique, They are a physical trait, physical characteristic of that particular element, the line emission spectra. You're going to be doing this in a lab. You'll be given one of these devices. You will have 3 different cathode ray tubes that we hook electricity up to, and there's a prism inside the device, so it will be bending the light, and you'll be able to see the different colors that it gives off as well as the different wavelengths. It has a measuring device inside, so you'll be able to see if it's 400, 500, 600, what the wavelength is for each one as well, so that you can see that they're all unique and different.